Okay. So continuing with the same example which we have seen earlier, let's say if there was this value, then it was something like L1, and then there could be something which is, let's say, B. So this L will be nothing but this L1, and then the value of B, which will be merged together. So this is how the value of L that is going to be calculated. And here now what we did was multiply by 2 and then plus the value of 0 which is added to it, right? So that is again remaining to getting the value 22. Okay, in this case, if it is this 0 present after that. Okay, so now what if no, there is a decimal point in the binary number? In that case, what will be the situation? Let's say if this is 11.01, then what is the appropriate value for this is this will be nothing but 3.25, that we know, right? And if I say this is 11 dot let's say 1101, then what is going to happen here is this is nothing but 2 to the power minus 1, this is nothing but 2 to the power minus 2, then 2 to the power minus 3, and then 2 to the power minus 4. In this way we are going to have the various no, after decimal point the values, that is nothing but 1 by 2, then 1 by 4, 1 by 8, and 1 by 16, and so on. So this is the general method as such which we normally know. So, but using SDT and the grammar, if you can follow any other method, then we are interested to see that, right? So let us see if there is any other alternative method which is existing. So let us see that using SDT, and if you can then prepare the SDT for that, so that would be useful to us. So let's say what we have seen is, let's say 0.01, right? And this is nothing but 1 upon 2 to the power 2, right? 1 upon 2 to the power 2 is nothing but 1 upon 4. Now, total number of digits, I'm talking here, total number of digits are 2 to the power 2 upon, this is the total decimal value of this is 1. That's why 1 upon 2 to the power 2 is 1 by 4, which is nothing but 0.25, right? So this is one small example. Let's say here if it is 0.11. So then in that case, what is the appropriate method, alternate method to find out what is the appropriate value for this is, let's say, in this case, what is the decimal equivalent of this is, let's say 3. And how many digits are there? So that is nothing but 2 to the power 2, right? So this is nothing but 2 to the power 2 digits. I mean 2 digits, and that value of digit 2, I mean total number of digits, I'm keeping it as the power here. So what will be the value? This is nothing but 3 by 4, which is nothing but, this is going to give you 0.75, right? So this is nothing but decimal value. This is nothing but decimal value upon the 2 to the power number of bits. 2 to the power number of bits, right? So this is how we are in a position to calculate the value after the decimal point, right? So for decimal point, there is a slight change in the grammar. So we'll see that small change in the grammar and the appropriate SDT for that. But before we go into the grammar, I think this concept was required. That's why now the decimal value upon 2 to the power number of bits. So if we can use this, then we can come down to a simplified solution using SDT, right? So translation of binary numbers with decimal values in between, I mean with decimal point in between. So what will be the case here is n will have L1 dot L2, right? L1 dot L2, that is decimal point which is there in between. And I mean L tends to, we know that it is the value which is, let's say, L1B, and the rest of the things remains the same. I mean, or B, and B can be either 0 or 1, right? It can be either 0 or 1, right? So what will be the action part for this, the appropriate SDT for this? L1 dot L2, right? So n dot decimal value is equal to L1 dot decimal value, then plus L2 dot decimal value, that is the decimal value, divided by 2 to the power number of bits, right? So divide by 2 to the power L2 dot C. If I say L2 dot C count, so then it would be this problem could be rectified. So even we will have the decimal part, that is if it is 11.11, so this decimal part is nothing but this, and this will be calculated using this two, right? So in this way it is going to be coming up into consideration. So so just to remove this, I mean to make it clear, right? Okay. So what about this second production? So L tends to C is equal to, I need to have the count also. So L dot C is equal to L1 dot C plus B dot C will be the required part for the count part, right? And as far as the decimal value is concerned, so L dot decimal value is equal to L1 dot L1 dot decimal value. We know it has to be multiplied by 2 plus B dot decimal value. So B dot decimal value, right? In this way, we are calculating the count also, and we are calculating the decimal value of the binary number also, right? And here, what it will be there, L dot C equal to B dot C, and L dot well equal to B dot well. So L dot decimal value is equal to B dot decimal value, right? So maybe semicolon everywhere you can put it. Okay. Then B dot C equal to count equal to 1, and the B dot the value for that is decimal value will be equal to what? It will be equal to 0 for this, right? And here I know that this digit also needs to be counted. So B dot C equal to 1. We have seen this earlier in the when we started with this binary example, that if both are 1, no, we can calculate the total number of digits which are present inside the binary number, right? Bits which are present inside the binary number. And what is in this case the decimal value for this? B dot dval equal to 1, right? So in this way, this would be the appropriate SDT for the translation on binary numbers with decimal point in between, right? So this is the actual grammar, and these are the grammar and the semantic rules. These are nothing but semantic rules or action. Semantic rules or actions that is going to be taken when the appropriate grammar is actually matched in the compiler, right? So what we will do is we'll take one example for this. Maybe I hope this example is no more required here. It is very much simple, and you can take it forward with taking some example and draw the parse tree, and then you'll able to figure out what is the appropriate number. So we'll take a different example, and that example would be, now enough of binary numbers. We'll take an example of generating the 3 address code, right? So SDT to generate 3 address code. SDT to generate 3 address code. So we know what is 3 address code, right? So let's say T equal to T1 equal to A plus B, then T2 equal to T1 plus C, and let's say X equal to T2. In this way, if this is there is some statements, no, then there are 3 operands which are there, and that's how the 3 address code would be represented, right? So what we know, what we need is that that we need the generation of somewhere temporary variables, and the values which will be associated, I mean values will be assigned to this temporary node. So what we would say is there will be some function which is, let's say, new temp. New temp is one of the functions which is going to generate a temporary variable, and once this generation of temporary variable is done, then the generation of this value will assign the appropriate value to the left hand side element, right? So let's say how this could be done, right? So let's say S tends to ID equal to E is the starting production, and then E tends to E or E plus, E1 plus T because I'm just differentiating it to be E1 compared to E, so that now it becomes easy for us. Or T, right? And T tends to T1 star F, T1 star F, and again T tends to F, and even F tends to ID, right? So this is a grammar for generating, let's say, 3 address code. And I mean, it is having an expression which is having plus and star and the variables inside it. So we need to generate the appropriate 3 address code for this. So what could be the possible semantic actions for this is, let's say, what it will do is it will generate the number id dot name, let's say, is equal to e dot place, something like this, right? And we'll use these values, attribute values, in this generation of this SDT. So let's say e dot place is equal to new temp. So new temporary variable will be created, and once this is created, it will directly go into the generate function, which is going to say e dot place equal to e1 dot place plus t dot place, right? So this is how it is going to be done, semicolon and bracket. And this is simple allocation, e dot place equal to t dot place, right? And likewise, here what is going to happen is t dot place equal to new temp. So new temp will be created, and it is going to call the generate function, which is going to assign t dot place is equal to what is that is t1 and f, right? So t1 dot place star f dot place, right? And then it is going to finish, right? And about for this f, it is going to be what it is very like t dot place equal to f dot place, right? And for this, what will be there? F dot place is equal to id dot name, right? Id dot name. So there is always anyway going to be some name associated, variable name associated to the identifier. So what I mean to say is there will be some temporary variable which is going to get created here, and this temporary variable would be then assigned some value from this which is an expression. So T1 equal to A plus B, something like that. And then here if you see T1 or T2 equal to A star B, sort of thing. All right. Rest of the things are quite simple, but if you are able to understand this, then your problem is getting solved. So let us see this with the help of an example. So let's say if x equal to A plus B star C, x equal to A plus B star C, then this expression is having 4 operands, right? 4 addresses. So our objective is to convert this into 3 address code, right? So this is I can say this is nothing but 4 addresses. 4 addresses. So I need to convert using this SDT into 3 address code. So what I will have to do first is I need to convert this into the appropriate pass tree, and from the pass tree I will be generating the appropriate 3 address code for it. So let us generate the pass tree for it. You can just remember this, and where we have generated the temporary variable at plus and at star, okay, and even at id equal to e, right? So x equal to the final value, let's say. Okay, so let's generate the appropriate pass tree for x equal to a plus b star c, right? So a plus b star c. So what will be the appropriate pass tree for this? So using the grammar which was given to you, so it will be like s is equal to id equal to E, S equal to ID equal to E, that is the starting production, and plus operation followed by star operation, but star has to be performed earlier, so we'll have that star on the bottom level, right? So E equal to E plus T, right? E equal to E plus T, and then T equal to T star F. So T equal to T star and F. Are you getting this? So there is going to be plus and star which we have generated and equal to operation which we have generated. And we want this ID to be there for all the A, B and C. So E tends to what? E tends to T, E tends to T, and then T tends to F, and F tends to ID, right? So in this way, so again here it will be T tends to F and F tends to ID, right? And F tends to ID. So what I will do here is, this is nothing but my value X, right? And this is my value which is A, my value which is A. This is my value which is going to be plus B, right? Plus B and star C. So this is C, right? So what will be the output, you know, when we apply the SDT onto this? So it will continue from, it will go in this way, and where it will go is, it will have to do the reduction operation. So F tends to ID. So F dot place will be equal to what? F dot place equal to ID dot name, right? We are having that SDT operation. So F dot place equal to what? Equal to again A, right? ID dot name, which is A, right? So this is going to be there here. So again, T tends to F is the reduction operation which is possible. So at this reduction, T dot place equal to what? F dot place. So T dot place equal to again A, right? F dot place, right? Are you getting it? So T dot place equal to F dot place. Here T dot F dot place equal to ID dot name. So it continued in this way. And what happened is this is going to see what? Again, E dot place equal to A, right? E dot place equal to A. So it will continue in this way. Then where is the reduction operation next possible here? It is possible at this. So what will happen is F dot place equal to B. So B will be stored here. Again, this dot place equal to B. So it will be done, and in this way it will continue. Likewise, when it will come here, F dot place equal to C. And at this place, there is going to be another reduction operation which is going to be there. So what will happen is, at this place, this operation is going to be executed first, right? So what will happen is, T dot place is going to generate a new temp, which is, let's say, T1, right? So T1 is generated. T1 is generated here, and what will be the outcome at this place? So after generation of this, it's saying that T dot place equal to T1 dot place into F dot place, right? So T1 is equal to B star C, right? So this operation is done first. So B star C after generating T1, right? Then it will continue, and this T1 is now available. So at this place, what will happen is A plus T1, right? So A plus T1, but at this place also it is going to generate a temporary variable. So E dot P equal to T2, right? So at T2 will be equal to E dot P and T dot P, which is equal to T1. So this is nothing but A plus T1, A plus T1, and so now T1 and T2. T2 is now a combination of A plus T1. So we have just calculated this, and entire operation is now available in T2, right? So this T2 is then supposed to be given to the variable X. So it will come here, and what will happen here is ID is X, and X will be given the value which is T2, right? So it will again generate this ID dot name equal to E dot place. So we'll do the generation, and we'll say that X equal to T2, right? So this is how the intermediate code has been generated for the 3 address code. 3 address code is generated basically for the given expression, right? So I think once you understand this, things are very much easy, and then you can be given any sort of expressions, and then you could be told to you that you generate the appropriate 3 address code for them for the same. So we have seen different types of SDTs till now. We have we can classify SDTs into 2 types. That is what we are supposed to see next. And what is there inside the SDT would be, it could be either the completely inherited attributes, or it could be like it is getting the value from the siblings. So both way the possibility could be there. Either it could be from the parents, the value could be available, or maybe from the siblings also it could get the value. So based upon this, there has been a classification of SDT into two types. One is known as S attributed SDT, and another is L attributed SDT. So now we will discuss this S attributed and L attributed SDTs. Right. So one is S attributed SDT and L attributed SDT. So SDTs are classified into two types, L attributed and S attributed. So before classifying SDTs, let us classify attributes first. So till now, we have seen that every variable is having an attribute, right? And an attribute associated with it. So what I'm saying is, till now we have seen that every variable is having an attribute associated with it, and it is getting some value, right? And based upon this, we are going to have two types of possibilities which could exist, right? So before we go into these details, so let us see, if I am having a production like A tends to, if I'm having a production like A tends to B, C, and D, right? And what is the meaning of this is, let's say if this BCD is getting the value, or maybe BCD is going to give the value to A. So that is one possibility, right? So this is which means that A is taking values from its children's, right? So such an attribute is called synthesized attribute. So if this is the case, then it is known as synthesized attribute, as attributed SDT, right? So from these children's, the parent is going to derive the appropriate value for it, right? So what I'm saying here is, it's like A dot S is equal to, is a function of let's say B dot S comma C dot S comma D dot S. So using this, if it is going to get some value, so we call it as S attributed SDT, right? And next possibility which could be there, which is an L attributed SDT, is something like the same thing. Let us take the same example, B, C, and D. And if we are at this, if C is taking its attribute from its parent, let's say we are talking of this C part, right? So if C is taking its attribute from the parents, so this is one thing which is possible, right? Or from its sibling. That means there are two siblings which are there, right? So C and D. So it can get the value from this also, it can get the value from this also, right? But the L attributed attributes, L attributed SDT, there is some difference. So the point is here is, let's say C is getting the value, taking its attributes from its parents or from its siblings, then such an attribute is called inherited attribute, because it is inheriting the value from the parent or maybe from the siblings, right? So what is the meaning of this is, attribute is let's say C dot I is getting the value from A dot I, right? So it is getting the value from A dot I, or maybe C dot I is getting the value, C dot I is getting the value from B dot I, right? Or again C dot I is getting the value from D dot I, right? So these are the possibilities which could exist, but in all such cases we can say that this is an inherited attribute, right? So once we know this types of different possibilities which exist, let us differentiate what is S attributed SDT and L attributed SDT. So we'll take that as a difference, and then we'll understand it. Okay, so S attributed SDT and L attributed SDT. So there are various differences which exist. So first one is, it uses only synthesized attributes. It uses only synthesized attributes, right? And this uses both inherited and synthesized attribute. So this uses both synthesized and inherited attributes. Right. And so each inherited attribute is restricted to inherit either from the parent or the left sibling only. So that is the only tricky part, and that's why it is, because it is only going to get from the left one. That is why it is known as L attributed, right? Left sibling only. So what is the meaning of this is X. Let's say if I'm saying this as example is, let's say A tends to XYZ. A tends to XYZ, then y, let's say y dot s will have the value from A dot s, and it can have the value from y dot s can have the value from x dot s. So both of these are correct, right? But it cannot have the value, that is y dot s cannot have the value from z dot s. So it can have the value from this, it can have the value from this, but not from this. So this is not possible, right? So in this way, these things would be there. So that is why it is known as L attributed. It is going to get the value from the left hand side sibling only, and not from the right hand side. Excluding the right sibling, it can get the value, right? So that is one thing. Second is semantic actions are placed at the right end of the production. So semantic actions are placed on the right hand side, on the right side of production, right end of production. I would say right end of productions, right? So what is the meaning of this is A tends to B, C, D, and I'm going to have the semantic action here, right? And whereas in this case, the semantic actions could be placed at anywhere on the right hand side. So semantic actions can be present at any place on right hand side, right? So what is the meaning of this? Meaning of this is I mean, A tends to semantic action here, B, C could be there, then A could be having B, then semantic action here, and then C, or even maybe A tends to B, C, and maybe here, right? So you can put the semantic action at any place. So it is more free, as far as the compiler design is concerned, right? So next is attributes. How the evaluation of attributes would be there. So we'll see that that in this case, it will be in the bottom up manner, and whereas in this case, the evaluation would be from top to bottom and left to right, and again. And once we follow that approach, we'll always make sure that the left siblings are seen first, right? So what is the meaning of that is, let us see that. So all attributes are evaluated. All attributes, attributes are evaluated in bottom-up manner, right? And what is the meaning of this? Let's say A tends to B, C, and D. This is the situation. Then A will get the value after traversing all the children's, right? So that is the meaning of that. So scan, it has already scanned all the children's by the time you reached A, right? So in this way, it is going to get the value. Right. So it is going to get all the values once it has seen all the children's, right? But in this case, what is going to happen is attributes are evaluated by traversing the parse tree. So depth first is going to take place, then left to right, and then bottom up evaluation is anyway going to be present, right? So what is the meaning of this? Attributes are evaluated. Attributes here attributes are evaluated by traversing parse tree, depth first, right? This is what is going to be the operation. I mean, it is going to see the depth first, then left to right operation, left to right, and bottom up evaluation. Understand? And bottom up evaluation. So anyway, bottom up evaluation is always there. Bottom up evaluation. Right. So what is the meaning of this is, let's say A tends to B, C, and D. If this is there, then it is going to come from the top to bottom and depth first, top to bottom, and then it is going to see, it is going to wait here. So all parents are seen, and all left subtrees are being seen or watched. That is the meaning of this. And you can see that now all the values which are available by the time you reach C, all values are available by the time you reach the value C, because all the left elements are supposed to be seen first, and then you are going to see the value of I mean, you are reaching at the location C to pass the tree, right? So this attributes, I mean, so it is not going to get the value from the right sibling. It is going to get the value from the parent, inherited parent, and the left sibling, and not the right sibling. So that is how it is going to create some difference in the S attributed SDT and L attributed SDT, right? So now that's all about the S attributed and L attributed SDT. Now let us take one example, and then let's understand the concept of S attributed and L attributed SDT in detail. Right. So this the examples which I'm going to discuss now, these are the examples which are asked in GATE. So refer to these questions carefully. And similar questions could be there in the exams. Right. So I'm giving you one example. Let's say first is, let's say E tends to LM. Right. E tends to LM, and what is the action part is L dot I. L dot I is getting the value, is a function of A dot I. Right. Is a function of A dot I, and that is one thing. Then M dot I is equal to function of L dot S, let's say, is there, and A dot S is equal to, is a function of M dot S, right? So M dot S. So this is what is there, and A tends to QR. If this is the situation, and these are the two productions which are there. So R dot I is a function of A dot I, and Q dot I is a function of let's say R dot I, and A dot S is equal to, is a function of Q dot S, right? So if this is the situation given to you, then the question is whether it is S attributed, L attributed, whether it is both, or whether it is none, right? So you need to find out the whether it is S attributed or L attributed or not, right? So the question is clear, no? So if you now you have to do what, you have to check it one by one. So L dot I is equal to function of A dot I. So is a function of A dot I. So it is not S attributed, because anyway it is inherited one, right? So this itself, we can say it is not S attributed. It is not S attributed, right? And what about the next one is M dot I equal to L dot S. So that is fine. That is L attributed, and even A dot S is equal to M dot S. Fine. So that is again getting it from the children, right? So that is S attributed. A tends to QR. What about this? So R dot I equal to function of A dot I, right? R dot I is a function of A dot I. So it is what it is. Is it L attributed? Yes, it is L attributed. So this is L attributed. And Q dot I is equal to function of R dot I. See, Q dot I, it cannot have the value from R dot I, right? So that means clearly this is not the L attribute. This is not L attribute, right? So not L attribute. And A dot S is equal to, it can get the value from Q dot S. Fine. So both the possibility exist in this. No, in this first production it is saying not S attributed. In the second production it is saying it is not L attributed. So answer to this is whether it is S attribute, L attribute, both or none. Answer to this is none. Right. So now what about this example? Let's say A tends to BC. A tends to BC, and I'm saying B dot S is equal to A dot S. So what is the answer for this? So whether it is S attribute or L attribute or both or none. So in this case, clearly no, it is getting B dot S from A dot S. So answer is L attributed because it is inherited, right? So now what I'm saying here is no. Observe that no, there is synthesized attribute which is S, and there is L attribute which is in this way. So if the grammar is S attributed, no, observe this. If the grammar is S attributed, then definitely it is going to be L attributed, right? But if the grammar is L attributed, it may not be S attributed. It may be or may not be, because no, it is having synthesized attributes and both inherited attributes, right? So we cannot say it is for sure that it is whether it is S attributed or not from L attribute, right? So this is all about the L attribute and S attributes and the syntax directed translation. So go through it a couple of times. You'll be able to understand it in a better way. I hope this topic is interesting to you. Thank you.